So here we have monochromatic light, which basically just means light with a single wavelength of lambda, shining on a metal with a work function. Yeah, and the wavelength of the light is varied, and for some wavelength, electrons are emitted from the metal. The maximum speed of the emitted electrons is measured as a function of the wavelength of the light. Derive an expression for the work function. Okay, so do you know the reference sheet?
The formula sheet. Thank you.
So we should be using this equation, the reference sheet, from the reference sheet. K max is equal to HF minus the work function. That's the equation to use here, basically. And also we should find the equation for the K, which is half mv squared. Let me see if it's somewhere here. Maybe not,
It's
but
at the end.
It's at the end?
Equals 1 over 2 squared.
Yep. Yeah. We should use both of these equations. So going back here, we're going to say that K max, because of V max, is equal to HF minus the work function. Now, what's the equation for K? Half mv squared. Mass of who? Mass of the electron, right? Because we're trying to emit an electron. V squared, so you should do V max squared. Okay. Now they're saying you should use the lambda, so we should convert that F into lambda. Now you guys should know that C is equal to lambda F, and so F is equal to C over lambda. So instead of F, I'll put C over lambda minus the work function. And they're saying derive an expression for the work function. So I'm just going to move it to the other side. I'll say work function is equal to HC over lambda minus half ME V max squared. Okay.
That's it?
That's the derive the expression, yeah.
Okay.
Okay. Now, it says when the light has a wavelength of this much, find this, the speed is this much, find the work function. So I'll apply the equation again to find the work function. So I'm going to say the work function is equal to, h is just Planck's constant, which you guys should know is 6.63 times 10 to the power of negative 34. It's found on the first page of your reference sheet. Same for the speed of light, it's given in the reference sheet, over lambda, which is 200 nanometer, means times 10 to the power of negative 9, minus half mass of the electron, 9.11 times 10 to the power of negative 31, and the Vmax is given to us as 6.5 times 10 to the power of 5, and you must square it, of course. Okay, and we will get the answer in joules. They didn't say to get it in joules or EV, so I'll just get it in joules. Right now, if you apply the numbers, you get it in joules. Let's see how much that is. So I got 7.5 times 10 to the power of negative 19 joules. Okay, but I only have one significant figure because this 200 here, it's a whole number and the zeros don't count. Just the 2 will count. If I have 1 sig fig, I must only end up with 1 sig fig. So you must round your number now to an 8. I don't know how strict they are with the sig figs. Just be careful.
You don't need to make it EV, right? Keep it joules.
Yeah, unless they ask, but they didn't ask. Triple I. The graph in figure 2 shows the maximum KE of the ejected electrons as a function of the frequency of the light. The original metal is now replaced with a different metal with a greater work function. So look, if we have a greater work function, would we need to exert less or more frequency than before?
More.
More.
So it has to be like forward.
Yeah, so look, if we have more work function, we need more frequency of light to eject any electrons. So just shift your line to the right side. So draw a line again from the origin, but now and make it, of course, parallel. They must have the same exact slope. That's not going to change. The slope is just h. I must shift it to the right side, basically.
Do we need to like pay attention to detail or anywhere up?
I would use a ruler if I were you.
But it doesn't matter where you place it, right?
No, as long as to the right.
Okay, that's
With this new metal, the students find that no electrons are ejected from the metal if they shine red light. Two students make the following proposal. Student A says, let's try a brighter red light. Student B says, let's use a green light. Which proposal is more likely to produce ejected electrons? So guys, look.
Student B,
Why?
because green has more. I don't
It's
know.
opposite? What do you mean by opposite? To eject the electrons, the HF must be more than the work function. And using brighter red light, which is student A, doesn't give more frequency, but student B says use green light, and you should say that the frequency of green is more than the frequency of red. How do we know that? Because red has more wavelength, because wavelength of the green is less than wavelength of the red. So more frequency means more HF, so it can be larger than the work function. Good.
So student B is correct.
Yeah, so student B is correct. Guys, if the capacitor is initially, is it charged? If it's initially not charged. So all the current goes to it. But finally, if it's fully charged, no current goes to it. That's the main idea here. So in circuit 1, the bulb will gradually increase in brightness. That means in the beginning, no current was going to it. All the current was avoiding it. And over time, the current will start to go to it. So let's go ahead. That's your battery. That is your switch. And now the current will choose to go between two branches, either the R branch or the capacitor branch. Now, of course, in the beginning, the capacitor is not charged. So in the beginning, all of the current will skip the resistor branch and it will go through the capacitor branch. Why? Because in the beginning, the capacitor is not charged. The capacitor provides you with a zero resistance pathway. So the current would actually rather go through the capacitor than the resistor. And that will make the resistor get zero current in the beginning. But then over time, as your capacitor charges up, all the current will start to deflect away from it and only go through the resistor, because now it's becoming fully charged. And that's why the resistor will start to become brighter over time, but not in the beginning. Okay, so they must be both in parallel with the battery in circuit 1. Shall I explain again, or do you guys get it?
I got it.
So in the beginning, all the current will go through the capacitor, avoiding the resistor, because the capacitor provides you with zero resistance. But over time, as the capacitor charges up, all the current will now start to go through the resistor, avoiding the capacitor. That's what circuit 1 looks like. In circuit 2, though, things are a bit different. In circuit 2, in the beginning, the bulb is going to be the brightest. But then, over time, the bulb will have zero brightness. Okay.
Do you need to draw the bulb also in circuit 1?
Bulb is just the resistor, by the way.
Oh, okay.
Yeah. So we're going to draw the EMF again. If in the beginning the resistor or the bulb was fully bright, it's because it was receiving all the current. So it had to be in series. And the capacitor was also in series with it. But then, of course, over time, when the capacitor builds up, it will block all the current. And that's why the resistor will stop receiving any current. Okay. So just to recap, initially, no light, but then finally, full brightness. That is in circuit 1. But in circuit 2, it's actually the opposite. In circuit 2, initially you start with full brightness, but then finally you end up with no light. Okay. The scientist designs a circuit consisting of a resistor of resistance R, uncharged capacitor of capacitance C, a switch, and a battery with a potential difference connected in series. Derive an expression for the current in the resistor immediately after the switch is closed. When the switch was just closed, does the capacitor get any current?
No.
No. So now we're going to say the potential difference in the battery is equal to the current that's passing in the resistor times the resistance itself. So it's R small I times capital R plus the current that's going in the capacitor, okay, which we don't have a symbol for. We're just going to say the voltage of the capacitor. Okay. Yeah. Now, when the switch was just closed, the voltage of the capacitor is going to be 0 when the switch was just closed. Why? It has not charged up yet. So essentially EMF is equal to IRI times capital R. So IRI is equal to EMF over the resistance. Okay. That's for part I. For part I, determine an expression for the current IRF in the resistor after the switch has been closed for a very long time. Now, if the switch has been closed for a very long time, what's going to happen is that the capacitor is fully charged. So EMF is equal to the voltage of the capacitor. So the IRF is going to be 0. Okay. Good. Now, on the grids in figure 1, sketch the current IR in the resistor and the potential difference delta VC across capacitor as function of time. So IR was in the beginning equal to how much? In the beginning we had EMF over R, correct? So here I'm going to be putting EMF over R, so it was not 0, but then over time it became 0. So we have an inverse relationship with time. If it's inverse, never use a straight line going down. Never. Always use a curving line going down if it's inverse. Okay. And over time, the voltage of the capacitor increased. Over time, we started at 0, but then over time we reached a full voltage. So we're going to be increasing over time. But it's going to be increasing in the beginning fast, and then it's going to be flattening out at some point. And it's going to be flattening out at exactly the voltage of the battery. Because at some point, like we said before, the EMF of the battery is equal to the voltage in the capacitor. Any questions?
No, good.
And they said label any intercept, which we did. That's the y-intercept for both of them. D. The scientist modifies the circuit from part B by adding a second identical resistor in series with the other circuit components. How would the Ri in the resistor immediately after the switch is closed compares with that? If you're adding resistors in series, what's going to happen to the R of the circuit?
Less. I meant more. The
More.
R would be more.
Exactly. So we're going to say adding a new resistor in series results in more R circuit. So V is equal to I times R circuit to keep V constant. If R circuit increases, then I decreases. So the current will be less. So I will now be less in the new circuit. Students are given a clear, rigid cylindrical container that is sealed with a movable piston. The piston slides with negligible friction and can be locked into place. The container is filled with 1 mole of gas and can be placed in a cold water bath to keep the temperature of the gas constant. The students have access to a meter stick and a pressure sensor that can be placed inside the container. They want to determine the relationship between the pressure and the volume if it's consistent with the ideal gas law. So first of all, P and V, how are they related to each other in the ideal gas law?
Inverse.
Inverse. So they want to determine if they're inverse or not. Describe an experimental procedure the students could use. Okay. So first of all, do we have to find the pressure?
Yes.
Yes, because we have to establish that over time, right? So, and we are given basically here a pressure sensor. So we're going to say use the pressure sensor to measure the pressure. So you must connect it to the container. Now you want to also establish the volume, and volume of a cylinder is equal to pi r squared h. So you're going to also use the meter stick, and use the meter stick to measure the height and the radius of the cylinder and the radius of the piston to find the volume of the cylinder. Now, of course, you are going to be pushing. Wait, they said that the piston is locked in place, or the piston can be locked in place, but it can also be sliding. So now it's your choice to pull up the piston or to pull it down. It's up to you. So we're going to say push the piston down to a certain height and measure the pressure and volume. Plot the points. Do this again for, you must have 5 in total at least, okay? For 4 more measurements of different height. Yeah. B. Describe how the student should analyze the data to determine if the relationship between the pressure and the volume of the gas is consistent with the ideal gas law. So look, if you were to plot P versus 1 over V, you expect it to get a straight line going up, right? You should. So you're going to say PV is equal to nRT. So P is equal to nRT over V. So Y is equal to mx. Y is the pressure. X is what you're varying, which is the volume. And the slope is the nRT. And that's for a line, right? So you expect a linear graph where the slope is nRT. nR nRT. Good, so the slope here is equal to nRT. Okay, very good. In another experiment, the students fill the container with an ideal gas and lock the piston in place so that the volume remains fixed at 1.5 times 10 to the power of negative 4 meter cubic. They want to experimentally determine the number of moles of a gas in the container. They slowly raise the temperature of the water bath and periodically measure the temperature of the gas and the pressure of the gas. You want to get a straight line whose slope can be used to find the number of the moles of the gas. So look, they're able to do what? They will change the temperature. So temperature has to be what? Your y-axis, right? Your x-axis, because you're changing it, right? So now imagine PV is equal to nRT, and temperature has to be the x-axis. and you're expecting changes in the pressure. So P is the y-axis. So P is equal to nR over V times T. So Y is equal to mx, with x being the temperature and the Y being the pressure. Okay. On the grid below, plot the appropriate quantities to determine the number of the moles inside. So look, the slope is going to be nR over capital V. Okay. And if we find the slope and we know the R is a constant, and we can find the N. Also, the volume was given. So now we should plot those points on the graph. Ready? With pressure on the y-axis and temperature on the x-axis. Let me take the points. Now, my lowest temperature is 310. So I'm going to start at 300. So that means that each big line is 10 points. So 300, 310, 320, 330, 340, 350. But for the pressure, my lowest point is at 102. Oh, sorry. Yeah, 102.150. And I will just say pressure times 10 to the power of 3 to make my numbers easier. So basically, I will just write 102, for example. So now my lowest pressure is going to be 102. So I'm going to start with 100. And I must go up all the way to 114. So I must make it by intervals of 5. 105, 105, 110, 115. So basically, each two big boxes is a 5. Now it's time to plot. So 310 with 102. So 310 with 102. This is 102.5. So it's going to be, I guess, somewhere here, probably. Okay. 320 with 104.600. So it's like probably somewhere here. Wait a second. So let's understand what's happening here. How many boxes do we have from 100 to 105? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 10, right? So I have 10 boxes are equal to 5. So what's a single box?
0.5.
0.5, right? Do we agree? So here, for example, when I'm looking for 104.6, that's like having 104.5, let's say, which is just here. Now, when they want 107, so look, that would be 105, 106, 107, 108, and 109. So 330 with 107.850. $340 with 111. 112. 340 with 111. Point 200, right? So like here probably. And now 350 with 114. So 113, 114. 0.300. So 350 with that. And now what do? We just have to try to match them with a straight line. You cannot hit all the points, but that's okay. Draw the biscuit line. We just did that. We plotted the points. So now we're good.
That's it? That's all they want?
No, now D says find... Okay, so now D says find the value of the N. We already know that PV is equal to nRT. And that P is equal to nRT over V, where T is the x-axis. And so the slope is nR over V. So now it's time to find the slope, to find the N. So how do you find the slope? You cannot really use points in the thingy. Okay, you cannot just use points. Second. Okay, now. So how do you find the slope? You gotta pick points that are on the graph. So like this one, let's say. So never pick the same points you already did. Never do that. Like pick points that are clear to you. For example, to me, this point is very clear, right? And maybe also, maybe this point is very good as well. Okay, so let's find out what these points are about.
So I can't take from the table anything at all?
No, never take from the table. You must use the best fit line. So here, what exactly is this point? Now look, from 340 to 350 are 5 boxes. That means each box is 2, right? So this is at the third box. That's going to be 346. So 346. Now on the y-axis, each box is... Okay, so that actually is 113. So we're good. But don't forget, times 10 to the power of 3. And that point is going to be...
328.
326. 107 times 10 to the power of 3. Let's find the slope. So 113 times 10 to the power of 3 minus 107 times 10 to the power of 3. 346 minus 326. Let's find out what that is. I got 300. So now my slope is equal to 300. Yeah. So I'm going to say my slope is equal to 300 is equal to N times R, which is 8.31. That's actually in your equation sheet, the first page, over the volume, which was given to us in the beginning of the question, is fixed at 1.5 times 10 to the power of negative 4. So now N is equal to, put that 8.31 down, times 300. And I got myself 5.4 times 10 to the power of negative 3 mole. And yeah, that should be it. Laser emits monochromatic light of wavelength that's incident lambda, that's incident on a diffraction grating with slits separated by a distance of small d. Okay, the first maximum of the pattern is a distance of x from the central maximum. The setup is then placed under the water. Now, first of all, we have to know what equation to use here. So basically, there's an equation in your equation sheet. Let's look at it. It's actually this one here. A lambda n minimum over L is equal to m lambda. Yeah. So well, actually, sorry, I meant this one. This one. And so we're going to say y max is equal m lambda L over small d, based on that equation. So y max m lambda L over small d. Now, in the water, is the wavelength more or less than the air?
There's more index, so there is
In water,
less.
less.
In water, the speed is less, so the lambda is less. But in water, the speed of light is less than the speed of light is less than in the air. So the lambda of the light is less in water. And so y max will be less if lambda is less, correct? And y max just means the separation or the distance. So distance will be less than. So distance xn will be less than x as a result. And of course, you must explain why the speed of light is less in the water. You're going to say because n of the water is more than n of the air. Now, the water has an index of fraction of n, and derive an equation for the ratio of xn over x. By the way, the xn here and the x is just the y max, but they used a different letter to confuse you.
So
Okay.
they want y max over y, basically.
They want the y max in the water over the y max in the air. So now look, we know that y max is equal to m lambda L over d. Now, we're going to say m is equal to 1. M is not given. Is it given? Actually, yeah, it's first. So m is 1. So you're going to say y max is equal lambda L over d. Okay. Now, as we know, n is equal to c over v. And c means the speed of light in the air, so lambda f. But v means the speed of light in the water, so lambda of n times frequency. Now, the frequencies will simply cancel, so n is equal to lambda over lambda n. N is equal to lambda over lambda n. Okay. Now, is the capital L changing?
No.
No. Is the small d changing? No. Only the lambda is changing. So we're going to say y max. Actually, now I'm going to say I won't call it Y max, I will call it X, right? That's what they want. So I'm going to say that Y max is direct with lambda. So the Xn over the X is equal to lambda n over the lambda. And now we just figured out that n is equal to lambda over lambda n. So that means if you have lambda n over lambda, which is the reciprocal, just put 1 over n. Yeah. Cool. Indicate if your equation in part B is consistent with your reasoning in part A. So we're going to say that the equation makes the ratio xn over x inverse with n. So more n is less ratio. So xn over x decreases when n increases. They're inverse, right? It's 1 over. And as indicated in part A, in the water, the separation decreases. So xn is less than x. So it's consistent.